I'm Z Smith. I'm with Eskew, Dumez, Ripple. I made up an abstract. So our firm is a firm of about 50 people based in New Orleans. About 70% of our staff are LEED accredited, but only about 10% of our work is LEED. So we're trying to infuse what we do with sustainability, whether or not there's certification involved. In 2014, our firm was honored with what they call the Firm Award, which is a way of singling out one practice each year that practices can look at. We are based in New Orleans, but we work all over the country. We work for a lot of different universities. I just got back from a project we're doing at Cornell. We opened a building recently at Georgia Tech that I'll show here. We've worked with some community colleges as well. And we do all kinds of different building types. So we have, a short attention span. So we work on performing arts buildings, research labs, office and conference centers, culinary programs, active learning classrooms, dorms, and student life projects. And our practice is, I guess, unusual that for a firm so small, we sponsor a research program within our firm. So we hire one or two full-time people each year to kind of help investigate a research question that we wished we could force ourselves to do our homework on, and so we make them do our homework for us and explain everything to us. So through that, we've examined topics of building performance, resilience, community engagement, health in the built environment, the intersection between civil engineering and landscape architecture to improve sustainability and resilience and make cities more fun, a deep dive on building envelope technology, sound and vision, and the perception of buildings. And then the theme this year is called Deep Impact Paths to Carbon Zero, because all of the announcements say that we have to get to net zero carbon operation in about 10 years, and we have to get to dramatically, it's better than drastic, dramatically better or lower carbon footprint of construction. And so what our research fellows are doing this time is documenting 12 case studies of what it would take. There are some projects that are on track for doing that. There are others where you could run the numbers and say, here's what it would have cost. Here's the least cost path to doing those things. And so we're going to be sharing those results out through conferences and also guides that you can download off our website. A first case study right now is a project that's under construction, getting ready to open actually in November, end of November. And this is the first case study to come out of that work. This is a multifamily, very bare bones, Spartan, low-cost, affordable housing for intended largely for veterans and veterans with children. It's 50 apartments, 1 and 2 bedroom. It is going to be a net zero project, and it will actually have the ability to island off the grid when the grid goes down, as it does with embarrassing frequency in New Orleans due to windstorms. And it was built for $164 a square foot. And so this is an example of the kind of work they're doing in terms of explaining that when you build a building, there's the kind of burp of carbon dioxide from when you made the concrete and when you made the steel, and if you had to cut down the trees to make the wood and so on. And then there's the carbon emissions associated with running the building every year. So if a building is a typical building, this is a typical multifamily building as we build standard practice in the US, and then it uses electricity and gas, and obviously there's emissions associated with electricity and gas. And therefore there's a little more carbon each year, a little more carbon. So the cumulative amount of carbon emissions is done through this, is sort of signified by this carbon life cycle plot. The goal that's been established by the Architecture 2030 organization is that they've set goals for basically about a 50% reduction or 40% reduction, you can see here, in the carbon emission of construction, and then net zero operation. And how they lay out a pathway to net zero operation is a mix of you make a good, efficient building, and then you operate it right, and then that building might have some on-site renewables, might have some solar panels on the roof, let's say, for most climates. And then the rest, if there are still net emissions, their plan is that you can basically buy into schemes where renewable power is being produced off-site. And they have a way of knowing that it's really actually happening, and kind of a way of buying into third-party certifications for that. So that's that middle line, that green line. This project actually has much lower carbon emissions of construction than standard multifamily, and it's a net zero operation. So once it's been built, the idea is that that's its life cycle carbon emissions for as long as the building stands. That's it. It's done. So the time will tell as that building goes into operation, but we're pretty hopeful. This is an example of the kind of analysis of typical construction where there might be concrete floor slabs, a very energy-intense building envelope, say brick or a Lucabond or something like that, and then the interior finishes. Every choice we've made here, we've made for lower carbon of construction. And of course, the real question is, what does that cost? And so this project was spec'd out to cost $153 a square foot, just trying to do things sensibly. And then through a series of upgrades to the HVAC and to adding solar and then adding battery backup, we've taken it to $164. So this is a very competitive price target. Now, obviously, that offset is an offset you could apply to fancier projects, less Spartan ones going forward. So that's just an example of what we're trying to do in our firm and what we're working with. There are a lot of great firms in this room that are trying to kind of pick up their responsibility and see if they can't improve their overall performance. And there's, as architects, there's what we do when we design, and then there's the rubber really hitting the road when the buildings are opened and operate. We have to work with facilities people who are the people who can have to, who can make a break, whether a building will perform as we'd expected. So the American Institute of Architects has created this thing they call the 2030 commitment. And as architectural practice, you can sign up for it. And what it says is that you will basically write everything down. You will enter into a spreadsheet or onto an online database every project you're working on that year and what building code you're building or energy code you're building it to, or if you've done an energy model, what you think the predicted energy will be. And it will add up the cumulative impact of all of your projects. And then they've set a set of goals where we aspire. I aspire to a full head of hair. I won't achieve that. But where you aspire to better and better performance every 5 years, the kind of bar gets raised. So in the gray bar here is the sum of all of the architecture firms that are signed up for this. Currently, those firms that are signed up are responsible for 30% of all construction in the United States. So even though it's only about 250 firms reporting, it's all the big guys who are doing all the big buildings. The green bar is our own firms tracking our own portfolio. And we chose, you're not required at all to make it public, we chose to disclose. Back when we first started tracking, and then we were tracking behind, but we were slowly inching up. And then as we kind of applied more and more and better tools, we found that our portfolio got better and better. And so we've been sharing what we've learned from that. So this is all about design. And this is about new buildings, major renovations, and even minor renovations where you're doing things like just lighting upgrades. You track it out. The other thing, though, that we think is important is that you should report out how the buildings really worked. So we get the utility bills for many of our projects. This one was built 20 years ago, and we're still getting the bills for it. And the little yellow number is the total amount of energy, gas plus electric, added together into BTUs per square foot per year. And we compare that with the bills for that building. And so some of the times we're really proud. It's significantly better than the average building that's out there. The government does, the Department of Energy does a big survey of the average energy use of these buildings. And it's sorted by building type because laboratory buildings tend to use a lot more energy, schools more in the middle, single-family homes, and then finally apartments, often the lowest of common building types. The one building type that's even bigger than laboratories is fast food restaurants because you've got all those deep fryers going in a small amount of area. But the energy use intensity, and sometimes some of our projects actually use above the median, but we think it's important. That's how we know we're not fibbing, is that we even, we'll show you a few of the firms that don't do as well as the average one. So that tracking of real performance and predicted performance is, we think, an important way for architectural practices and clients working together to do better. But I want to back it up and actually say, sometimes you forget, what were we actually trying to get done? Why did we build these buildings in the first place, right? Well, we want buildings to keep us comfortable, because there's no sense having a really low energy building if no one wants to go in there. People hate it. And we want to provide a good environment for working and learning, especially almost all of you here are involved in educational institutions. And we want to promote health rather than illness. And all that at the same time, we want those buildings to be affordable to build and operate and to maintain. We want them to be responsible with energy and water. And we want them to be future ready. We're doing a courthouse for the federal government in Mississippi. One of the interesting things is that it's kind of very deep in the regulations, is you're required when you design a building for the federal government now to actually map out, decade by decade, for the next 80 years, what is the anticipated climate and how your building will be adaptable to that. And so, for example, in Greenville, Mississippi, where we're doing this courthouse today, on the typical year, there are about 30 days a year when the temperature is above 95 degrees. The current predictions, based on best available science, is that by the end of the century, there will be 140 days a year above 95 degrees. And so you have to say, okay, well, what does that do to the duct sizing? What does that do to the cooling plant? And so on. So that notion of planning in resilience is kind of our responsibility. And those of you who are on the owner's side, specifying a building, it's, in a sense, irresponsible to not require your design team to tell you what the heck they're going to do when these systems have to get changed out. So, have you provided enough area on the roof for the cooling condensers that you're going to need? But another thing that we should do is start talking about I'm going to flip through these, talking about supporting, one of the things we need is thermal comfort. One of the really interesting things that's just come out in the last year or two is they finally started, it used to be that they would do, when they did a lot of psychological and learning measurements to keep it easy and controlled, they would only use men as test subjects. And so we have all these curves about what qualifies as thermal comfort and so on. They're all based on men, particularly college students, particularly in Iowa. That seems to be the hotbed of when a lot of this testing happened. Recently, this was a study, this happens to be with people in Berlin of a range of ages, but they did a whole bunch of tests on math, cognitive reasoning, and verbal performance, and they scored it, and this is the median score. Of course, there's a huge distribution, there's a huge spread, because we're all different. Not all women are the same, not all men are the same, but they did notice that there's this particular shift, which I noticed in my office, and I don't know if you notice in yours, is that on average, women tend to report being colder. It's not just that, even at the same level of clothing, they'll report feeling colder than men. And if it's men in charge of the thermostat, you can imagine what the impacts of this can be. So as we start to think about making good spaces for learning, because this is an institution of learning, it's very clear that there is an impact on performance with temperature. And what's even more interesting is how do we provide, given that we're going to have a room full of people, and not all women have the same point of comfort, not all men do. So one of the interesting shifts that's happened is people are starting to say that actually they want you to plan not for a uniform temperature across the room, but deliberately a variation in temperature. So the people who are comfortable with a cooler and work best there can sit over there, and the people who are more comfortable with a little bit warmer can sit over there. Now that's in contradiction to everything every engineer has ever been told they're supposed to do. They're supposed to achieve complete uniformity. In fact, that's a measure of success for them. So the well building standard has started to say maybe let's look at non-uniformity. Light. There are a lot of good double-blind peer-reviewed studies now that show that daylight helps make you smarter, keeps you more alert. So for example, in a study of several hundred California schools, controlling for all other influences, they found that the students who had their classes in classrooms with the best quality of daylight progressed year over year 20% faster on math tests and 26% faster on reading tests, compared with the students who were in the classrooms with the least. Similar one, office workers with good views performed on an average 18% better than those with no views, and call center workers actually got through more calls, were able to successfully resolve calls faster. This was done at the Sacramento Municipal Utility District, where you call up to start your service, you call up to cancel your service, you call up to resolve a bill dispute. And they have 10 or 20, I don't know how many call centers they have, and they were just rented randomly. There was no big design to it. But this team of researchers came in and noticed how different call centers had different kind of productivity rates. And then they correlated that with the physical environment in those different spaces. So it makes a difference. This is a really funny study. This is done at the University of Oregon, and they looked at the main student services building. And they had people, they just stopped passersby, and they showed them pictures. They took pictures standing in front of the windows looking out. And so they took kind of 10 representative views out of the building. And then they asked passersby, which view do you like? Do you prefer, A or B? Compare C and D, compare E and F, and so on. And from all that, they get a rank-ordered spectrum of the nicest views to the least appealing views, straight into the cooling tower or whatever it was that the worst view was. And then they anonymously got the health records and absentee records, where they just were sorted by where those people sat and what view they had. And what they found was that the people with the worst daylight quality took on average 2 more sick days a year, and the people with the worst view took on average 1.4 more sick days a year. So these things that we think of as luxuries or amenities actually have, if you think how much a sick day costs a business, these have real financial impacts. But now I want to talk about, since we're all talking about carbon dioxide, and we're all talking about global warming and climate change, so we all know that right now, when I was born, now on 60 years ago, carbon dioxide levels outside were around 250, I think, parts per million, passing 300. Now we're at about 410 parts per million. And when I was growing up, I watched that Star Trek. There was in the keynote, there was that talk about the original Star Trek, and there was always like when the life support system shut down, and the people were like, oxygen, I need oxygen. And yet the funny thing was, with Apollo 13, a few years later, it wasn't that they were running out of oxygen. They had plenty of oxygen. What was happening was that when we inhale oxygen, we metabolize and we exhale carbon dioxide, which means the carbon dioxide level would normally go up. So rather than carry a greenhouse behind them on the spaceship, they had these special filters which just basically absorbed carbon dioxide. And their problem was that their filters that absorbed carbon dioxide, the system was broken or they didn't have enough of them. And so you remember the great scene from the Apollo 13 movie where this guy says, we need to get, the landing module had one format carbon dioxide absorber filter, and the main capsule had the different one, and they had to make one fit to the other. So this is what they actually did. And of course, the most important component that they had on board was duct tape. And so they made that whole system work. But that's just to tell us that indoor carbon dioxide levels, if they get too high, will kill you. Now, a series of studies were done recently in Schenectady, New York, at a research center, University of Syracuse, that's it. And they built this amazing facility. So that's what's upstairs. It looks like corporate America, windowless, boring cubicles. But that's what's below. Every single one of those cubicles, they could change the air quality, the amount of carbon dioxide, the amount of volatile organic compounds, VOCs. And then they invited in test subjects over the course of a week, 6 days, 8 hours a day, and they had them basically playing a game, not a video game, but a game in which you are a city manager. And you receive a series of emails, and there's a fire at the tire plant, and there's a problem at the school, and there's a this and a that. So you have to go find out, there's a fire. What's in that plant? What's that chemical? What are the risks? Should we use water or not to put it out? And so you have all these tasks to go doing a lot of analysis and figure out what you should do next, and it requires a lot of higher cognitive function. And then they varied and they tried the air conditions, the conditions of the air that are found in most conventional offices. And then they said we're going to do like a LEED building where they made a lot of effort to have low VOC indoor materials, but are still ventilating according to the current standards. And then just for interest, they tried a much higher rate of ventilation in which there was also low VOCs, but also higher rates at which outdoor air was flushed in. And so the indoor carbon dioxide levels were lower. And what they found was astonishing. These, again, are the conditions, what they call conventional, and there are numbers associated with this. Outdoor levels are around 400 parts per million now. Indoor levels, according to current best practice, if everything's running right, are typically between 1,000 and 1,100, 1,200 parts per million. And then they tried what they called enhanced green, where they flushed air about 3 times as fast as normal and got the indoor carbon dioxide level down to around 550 parts per million. So they run that experiment, and then they tried all these different tests. And they have a lot of different tasks, and I won't go through them all, but information usage, information seeking, searching, crisis response, and so on. And then they score you. How long did it take you to find the right answer? Did you ever find the right answer? And so on. And then they just normalize to each of these categories, whatever score you got under typical office conditions, and they compared the score you get in a green building and then what score you got for that task in an enhanced green building. So you'll see on the ability to use information using both provided information and information that has been gathered towards attaining an overall goal, the people in these conditions got a score 3 times higher on that one measure. And so there's this range of different tasks, down to ones where you're just looking for information, Googling, something we're all good at now. There was only like 10% better, maybe barely noticeable. But averaged over all of the tasks that we ask knowledge workers to do every day, a huge difference. In fact, they said, if you could hire somebody, suppose you weren't changing the conditions of indoor air, but you had 2 employees, you had 3 employees you could pick from, one who got these normal scores, one who got these scores, and one who got these scores. It's like that infomercial, how much would you pay? How much more do people who perform that much better get offered as salaries? And the answer, they used the Bureau of Labor Statistics, and they found that difference, you would have to pay $6,500 a year more in salary to get somebody who was that much better at those mental tasks. So when we talk about how much is a green building providing good, fresh, good air quality worth, it's worth, if you're not going to make your building provide that good air quality, you're going to have to go and hire a much smarter person and then stick them in your mediocre environment. So conversely, presumably, this maps to productivity and so on. So to put that in context, well, if we're providing all this much energy, if we're providing all this air, won't that cost some energy? And these scientists who did this work summarized their work, and they said, well, if you don't do anything clever with recovering the energy of the air you're flushing back out, and it depends on your climate zone, that might cost you as much as $40 a year per employee. But remember, they just said that you're going to get a value of $6,500 a year in better productivity out of that employee. Now, if you apply good energy efficient technologies, like we use in some of the buildings here in Dallas with energy recovery, we're recovering the dryness and the coolness, let's say in the summertime, of the air that we're flushing back out so that it can kind of pre-temper the air that we're taking in. That cost can be dropped in half. So what I want to do is show some buildings where we're applying these results. This is a building that just opened up, a project that just opened up in Georgia Tech. This is an office building for the people at the university who manage all the research. They manage $800 million a year worth of research contracts. And they also wanted to have a conference center for their own employees, but also to be a resource for the rest of the university. And they were in the middle of scraping up 7 acres of surface parking, so we stacked it into a parking deck. And then the third thing is the water rates that they pay in Atlanta are outrageous. And so there's already something like this at Emory University where they're actually harvesting the sewage and getting non-potable water that they can use in the campus cooling towers can be purified to the level that's suitable for use in cooling towers and saving them money. And so this project hosts all three. But the thing I'd call your attention is that cost, this building was built for $275. The office building component was built for $275 a square foot, which for a university building is it was very economical. It's cheaper than the average building at Georgia Tech. So we call those studies I was telling you about before, the CogFX studies. So we get to that level of air quality at a low energy cost. In fact, there's a green building standard called ASHRAE 189. It's structured just like LEED. It's just that there's no certification process. It's a standard enforced by your code official. And they've adopted that as their standard at Georgia Tech. On energy, it has to be at least 25% better than the most current energy code. And so it met all of those targets. And how we managed to get that cost down included like working super closely with we wanted to do solar shading. And the typical way is you just order up a whole bunch of aluminum fins. Aluminum fins are really energy intense to make and expensive. And so we worked with a local vendor of standing seam roofs, and we designed a way to achieve that same look and performance using just break metal forms. That's new construction, but I also want to talk about applying these approaches towards getting better energy performance on 20, 30, 40-year-old buildings. This building on the left here is the external view. We did a renovation of about half the floors of this building in the downtown medical campus and called the JBJ Labs project. And we did this, so this is a lab renovation. Now, labs typically cost new construction $500, $600, $700 a square foot because there's so much stuff going on in a lab building. This renovation was done for $158 a square foot. And so we took these windowless QB labs and blew open all the walls. That glass before that you saw on the outside view, that was glazing that you only got to see if you were in the corridor. Because the building was designed at a time when they thought that looking out the window might distract the scientists. So we blew all that open, and we made it so that this building is plug and play. So each of those lab benches actually just gets all their stuff that they need from the ceiling. And if you want to play a trick on your fellow scientist, you can pick up and move her lab bench to another end of the building and plug it back in, and so on if you want. That's really about adaptability, to keep the overall life cycle cost of running such a building and maintaining and modifying it as low as possible. We opened up all this glazing, and they said, but won't that cause glare on the south side of the building? And so this has the first installation in the state of, it's just motorized blinds that just come down and tilt according to where the sun is, a little sensor on the roof. And so we said, no, we can keep people, give them a view, we can give them sun when they want it, and it's under automatic control, but you can override it. And so that kind of a notion also allowed this building to have, basically we were able to cut the energy use of this about in half. We also had to argue with the regulatory agencies because at the time, there's this thing called the National Institutes of Health, and they espoused building standards for government research labs. And they had this standard that required this outrageous level of light in every, back here in the corner, you needed to provide 75-foot candles. And we said, how about we provide 75-foot candles on the workbench, and we'll provide an ambient of like 25-foot candles everywhere else where we're just walking around. And they said, oh, okay. And so they then updated and changed the standard. So part of the game of a good owner and a good design team is working with the standards organizations to get more realistic standards and performances. The other thing we did in this context was we couldn't blow open the entire floor plate. We just took the bays of the building that were nearest where all the glass was, and that's where the people spend all their time. And then the room where they keep their microscopes or their incubators and so on, those, it's okay to keep those ones to be windowless. So it's sort of targeting where you're going to spend your money. The next project to show like a historic renovation. Can you do this on really old buildings? Because Dallas has some very impressive really old buildings. So this is the Elks Club on what is called Elks Place, actually in downtown New Orleans. And the Tulane School of Social Work was up on the leafy campus uptown, but they wanted to move downtown because this spot turns out to be the best bus-connected place in the city. There's like 8 different bus lines that come together at this point. So for a lot of their practicums where they're integrating with different neighborhood organizations, they wanted one that people could afford to get to quickly and cheaply. And so that's a little bit like the El Centro campus in DCCD, which is very well connected by transit, and a lot of their students use transit. So we took that building and kind of did a radical rethink on the inside of that building. So we wanted it to feel modern and interesting on the inside, but we also went through and changed out the glazing units. We replaced them with low E. We were able to build a new insulated wall that manages moisture and manages cut way down on infiltration into that building. And we were able to use lighting really strategically in that way. And the biggest thing I'd say of why we were able to do this for also around less than $200 a square foot, more like $150 a square foot, was, so we took this essentially windowless experience, which had all been chopped up, and turned it into this kind of an experience. And we were able to do that was that when you're working in an old building, the biggest risk at bid time is the contractor feels like, I don't know what's inside this building. When I open up those walls, there'll be a pipe and I didn't even know it was there. I'm seeing nods of recognition. So we convinced the owner to actually break out demolition and let a contract for demolition to gut it down to clean interior walls. And then we did a walkthrough and we held the pre-bid meeting inside the gutted space. And that helped the contractors have much greater degree of certainty about what it was really going to cost to do this upgrade. Simple rules for what could be applied, and you're from all over here, not just DCCCD. The first one I want to call, because we've got people who are into buildings operations here, is that individual choice or operator choice it has a huge impact. This is a survey of 50 schools. There was a big school building boom in the late 60s, early 70s in the Toronto metropolitan area. They built 50 schools. They had a pattern template that they used, and they would change where the entrance was, but it was essentially the same design, modified for 50 different locations around the metropolitan area. So they were all about the same time. They all had about the same budget per square foot. And then they finally pulled together how much they were actually spending on utilities for each building. And intriguingly, what they found was a 3-to-1 variation between the most efficient school in energy use per square foot per year and the least efficient one. Remember, same building type, essentially same building design, same climate. These were all operational choices. When the principal of this school was told, this is your school, within 6 months, she moved her school to the middle of the pack with low-cost, no-cost interventions. Just people paying more attention. Now, principals have a lot on their plate, right? And part of it is just informing people what where they stand can have a huge impact. It's not about shaming. It's just like, oh, it's possible. That's the big secret, is that it's possible to make a building that runs at that much lower cost. And there are a lot of school districts that wisely, famously the Powder River School District in Colorado, that basically said 3/4 of all the savings flows right back into your budget, principal. And so it became this, like, not a profit center, but it became a center for getting all the discretionary money you wish you could have for programs. So you aligned people's shared savings results in a shared benefit. So operations choices matter. For new construction or major renovation projects, just designing to the most aggressive energy code that you can makes a big difference. So this is the, if I just set as 100, this is the average of all different building types. If I, just for reference point, they did a big survey of all the existing buildings back in 2003. And then when they promulgated the 2007 ASHRAE code, which becomes the International Energy Conservation Code of 2009, and so on down the line. You can see this one always follows that by 2 years. When they did this, they said, hi, if we built the average buildings but to this new code, this is their energy use. We'd save 31%. And so on. With each progressive improvement in the code, the market basket of buildings out there will use less and less energy. So as an owner, it's true that right now in Louisiana, this is the energy code. Right now, California is an energy code way out here. Texas is based on the 2015. And Dallas and so on, they're all there. San Antonio has jumped one, right? So it's up to a municipality. And that's by law. But as an owner, you have the freedom to just say, we want our buildings to be designed to the most recent code. So even if the rest of Dallas says it's the 2015 IECC, you could just say, put in your RFP, by the way, this building's going to be designed to the 2018. Right? And so you will enjoy, it's not nothing. It's kind of 8% better energy savings. And what that means is, especially for the small projects, the simple projects, if you're doing a big $50 million, $100 million building, then you can put on our propeller beanies and do energy models and all kinds of fancy tuning. But the energy code is set up with prescriptive requirements. It just says, if nothing else, if you're in this climate zone, use this much insulation, use this kind of a window, and so on. Don't use more than this amount of glass. That's the big one for architects. Bad architects, always trying to make glass boxes. And so if you follow the prescriptive requirements of the most recent energy code, you'll enjoy better and better savings. So that can make a difference. So in summary, I'd say that requiring the most aggressive code that you can for your projects makes sense. And require, based on what I showed earlier, daylight, views, and a higher than normal amount of fresh air per person for the people who are actually there. We don't need to provide all this air at 2 in the morning if there's nobody there. So we have to make buildings become more responsive. So right now we've got 15, 20 people in this room. So we need, say if we had 20 people, we need 800 cubic feet per minute of fresh air in this room. When it has 150 people in it, or if it has 100 people, we need 4,000, right? So we need to make buildings become more responsive so that we can deliver it rather than what we've found is in many buildings, there's no actual increase in the amount of fresh air that in terms of the capacity, the maximum capacity that the building needs. It's all about sending it where it needs to be. So we've, one of our things has been finding ways to work with mechanical engineers on that. I started to mention at the beginning of the talk the idea of embodied carbon. This is the thing people, especially in historic preservation, have been saying forever, which is, the most sustainable building is the one that's already there. But it's people have started to do the math. Right now, about 30% of all carbon emissions worldwide is traceable to the operation of the buildings that exist, the electricity, the gas they use. Another 10% of all the carbon emissions worldwide are the buildings we're building this year. It's the carbon of construction. So for that 30%, well, those buildings are all there, and we're only like adding 1%, 2% per year. So if we made every building net zero for the next 10 years, the impact, that's nice, we feel better about ourselves, but the impact will be very modest. On the other hand, if we cut the carbon intensity of every building that we're building, the carbon of construction, in half, which seems achievable just by being careful about stuff, that's this huge effect. That's like cutting global carbon emissions by 5%. And that's under the direct control of the people who are specifying new construction and the architects and structural engineers who are writing the specs. So getting our head around embodied carbon is like the new big thing. When people have suddenly realized that given how much carbon we are allowed to keep throwing into the atmosphere before the temperature exceeds certain limits at which they're worried about it will spiral on without any further help from humans, that carbon budget, a significant fraction of the total carbon budget of how much we're left to build is traceable to our building materials. Because things are happening already that are kind of for free, which is that Texas is the largest generator of renewable energy in the country, apart from old hydro stations. California's ahead on that. But in all other regards, Texas swamps California, swamps every other state. So your grid is getting cleaner every year, more and more wind mostly, some solar coming online. In Colorado, solar with battery storage is cheaper in open auctions than the cost of operating the coal-fired power plants that already exist. So it's cheaper for the utility to just not bother to fire up the coal power plant, to just take new solar with batteries to get through that. So this transition's happening. So for our electric grid, there's a certain amount that's going to happen for free if our buildings are electric. That's another thing that certain municipalities are starting to do, where in California, they've banned new hookups of natural gas. Because they say the grid's going to get cleaner. If you build that building that it can only use natural gas for heating, like you're not going to come rip out the boiler 5 years from now. And so the whole question is, how do we start to make the buildings to work better with renewable power? So, and that's not bad for the future of Texas. Like I said, Texas is the Texas of wind energy, right? And so Texas has a great future in this world, and so you're not being anti-Texan to make your buildings all electric. You're making them future-forward Texan. The part that the rest of the country is going to be lining up to buy is the renewable power that Texas generates. And then this one, I'll put a plug in, and this is harder in contracting, which is we should reward. I told you the story of the school district that rewards the principals and the teachers who help their buildings use less energy, and their operations staff. That money flows back to that school. So that's shared savings. You get this benefit back. Wouldn't it be neat? We all know of buildings that were claimed that were going to be super green, and when the bill came in the next year, turned out to not be so. And there's always 10 different reasons that may have happened, but the biggest reason is that there's no penalty for making a building that didn't actually perform like the prediction said. And so if we made it a game of there's a government research lab, big building, $100 million building, where they held back $3 million of the $100 million budget as reward for how well the building performed after 1 year. And they distributed that to the contractor, to the building operations staff as bonuses, to the architects and engineers who designed that project, and said, there's this pot, but you only get at that pot if this building hits the target. Suddenly, everyone's goals were aligned. And so we need to structure the bids that we're doing when we're seeking new buildings and major renovation projects. If we get everybody's incentives in the right place, what is it? You grab their wallet and their hearts will follow. So I think that's a big opportunity. So with that, we have about 5 minutes left, and I thank you. And I'd love to hear any questions or stories you have from your own organizations. Thanks.